Before we begin, take a moment to get comfortable. Let your arms go heavy, your breath slow. And as you listen, feel free to leave a comment sharing what time it is, where you are, and what city or village you're listening from. It's love to know. And if you'd like more quiet stories like this one, don't forget to subscribe so they gently appear when you need them most. Now, let's begin. Tonight, we begin quietly, drifting through the early universe. In the beginning, there were no galaxies, no spirals stretching their arms across space, no clusters, no collisions, no glowing cores. There was just ... expansion and silence. Roughly 13.8 billion years ago, our universe emerged from what we call the Big Bang. Though it wasn't an explosion in the traditional sense, it was the rapid expansion of space itself. In the first moments, the universe was hot, too hot for atoms to exist. Instead, it was filled with a dense soup of energy, photons, quarks, gluons. Over time, thousands, then millions of years, things cooled. Energy slowed down enough for quarks to bind into protons and neutrons. Later still, those protons met electrons and formed the first atoms, mostly hydrogen, a little helium, and an even smaller trace of lithium. But even now, this early universe was dark. Light couldn't travel freely, still bouncing off particles like a fog. It wasn't until about 380,000 years later that the fog lifted. A period called recombination. K-atoms became neutral. Photons could finally stream outward. That's the light we still see today as the cosmic microwave background, a faint glow that stretches across the entire sky, kind of fossil imprint from a time before galaxies existed in this dark, cooling universe. Tiny fluctuations in the distribution of matter were starting to form. These were incredibly small regions where the density of particles was just slightly higher than the space around them. But gravity noticed, and over time, gravity amplified those differences. More mass meant more gravity. More gravity pulled in more matter. So began a slow, deliberate collapse. These early clumps, some just a few light years across, are the ancestors of galaxies. They grew from almost nothing, from small ripples in the distribution of hydrogen gas spread across the young cosmos. And though it took hundreds of millions of years, these clumps grew dense enough to collapse under their own gravity. Inside them, pressure and heat rose. Then, one by one, the first stars were born. Not like the stars we know now. These were population 3 stars, ancient, enormous, and unstable. Some may have been 100 or even 300 times the mass of our sun. They burned hot and fast, and they lived short, violent lives. They lit up the darkness, initiating a period known as the cosmic dawn. With them, galaxies began to take shape. But this wasn't a neat process. It was chaotic. There were no spirals yet, no elliptical forms, just growing halos of dark matter, invisible scaffolding that formed the foundation of what would become galaxies. Inside those halos, baryonic matter, the ordinary stuff of protons and atoms, collected. Gas cooled. It condensed. Stars began to form in clusters, then disks, then shapes. Even at this stage, most galaxies were still small, what we might now call dwarf galaxies, but they were active, bursting with star formation, each galaxy building itself from gas, gravity, and time. Galaxies didn't form in isolation either. They gathered in filaments, long strands of matter stretching across space, connected like threads in a cosmic web. These filaments fed gas into the growing galaxies, allowing them to keep forming stars. And eventually, galaxies began to merge. Collisions in space may seem violent, but in the vastness between stars, they're mostly quiet. When two galaxies merge, their stars rarely collide. Instead, their shapes distort. Their gas clouds compress, and that compression triggers new waves of star formation. These mergers were a key part of how galaxies grew. A small galaxy might merge with another, or a dozen others over time. This was, and still is, one of the main ways galaxies assemble over the next billion years. Some galaxies evolved into the familiar shapes we know today. Spiral galaxies, with elegant arms of dust and stars curling outward from a central bulge. Elliptical galaxies, more spherical, with older stars and less gas for forming new ones. Irregular galaxies, distorted by past collisions or turbulence in their youth. But it all started with dust, with cooling gas, with gravity pulling the universe's first atoms into slowly orbiting, glowing structures. Even now, as galaxies continue to form, in the early universe, galaxy formation was fast and dramatic. But today, the process is quieter, more stable. New stars still form in our Milky Way, around 1 or 2 solar masses per year. But it's nothing like the furious birth rate of the early cosmos. The universe is aging. Galaxies are aging. Dust that helps shape them now dims their light. But the shapes remain, and they continue drifting through the cosmos, quietly evolving. They drift, yes, but not alone. The universe, even in its coldest stretches, is threaded with invisible forces. Gravity is the most dominant of these at large scales, patient, persistent, and undeterred by the distance between things. Galaxies are not isolated islands. They are nodes along the great filaments of the cosmic web structures so vast that they stretch for hundreds of millions of light years. These filaments are made of dark matter, mostly invisible, silent, but powerful. Dark matter doesn't emit or absorb light. It doesn't interact with electromagnetic forces, but it has mass, and mass means gravity, and gravity, as always, means motion. As dark matter collapsed into enormous halos, it pulled regular matter, the protons and atoms, along with it. That regular matter cooled into gas, and that gas, in turn, collapsed into galaxies. Some galaxies found themselves near intersections of filaments, places where matter collected more readily. These regions became galaxy clusters, immense congregations of hundreds, even thousands of galaxies, all bound together by a common gravity. Well, between them, thin threads of gas and dark matter connected clusters to clusters, and galaxies to galaxies. The structure is vast, but it is also intricate. Galaxies do not sit randomly in space. They follow patterns formed billions of years ago, shaped by the density fluctuations left behind by the Big Bang. Within galaxies, a different kind of structure took form. In spirals, like our own Milky Way, the stars arrange themselves into a flat, rotating disk. This disk often has a central bulge, a dense region of stars, sometimes surrounding a supermassive black hole. The arms spiral outward, not like spinning blades, but more like traffic patterns. Stars orbit the center at varying speeds, and density waves form. These are the spiral arms we see. They are not fixed structures, but moving patterns, constantly refreshed by waves of star formation and collapse. Elliptical galaxies, by contrast, are less structured. They tend to form through large mergers, when two spirals collide and their stars are stirred together into a more rounded, random motion. They are often reddish in color, as they contain older stars and little gas to make new ones. Without gas, there's no fuel for fresh stars, so these galaxies age quietly, glowing with the long, slow burn of ancient light. Irregular galaxies remain the chaotic ones. Some are young and haven't settled into a shape. Others are disrupted by interactions, tidal forces, collisions, or near misses that distort their structures. Some have strange arms, lopsided bulges, or are stretched like taffy by the gravity of a passing neighbor, no matter their shape. All galaxies are bound by shared properties. Each one has mass, from its stars, gas, dust, and dark matter. Halo. Each one has momentum, spinning, moving, falling through the universe's expansion. Each one evolves slowly, imperceptibly, through collisions, star formation, and the quiet death of stars. The life of a star is at the heart of galaxy evolution. In young galaxies, gas clouds, rich in hydrogen, collapse under their own gravity. These clouds fragment into smaller cores, which form stars. Some stars are small, cool, and long-lived, like red dwarfs. Others are large, hot, and short-lived, like blue giants. The most massive stars burn through their fuel in just a few million years, and then they explode. Supernova are more than endings. They are redistributions. In a single moment, a star can seed its galaxy with elements, carbon, oxygen, iron, and beyond. These elements enrich the surrounding gas, making future generations of stars more complex. The first stars, those population 3 giants, had almost no metals, just hydrogen and helium, mostly. But over billions of years, through countless generations of star birth and death, galaxies became chemically rich. Now, stars like our sun contain traces of many elements, planets, life, even human bodies, owe their composition to generations of stellar recycling. Galaxies, then, are not just collections of stars. They are ecosystems. Gas flows in from outside, from intergalactic filaments. Stars form within. Supernova push gas back out into the galaxy's halo, or even beyond. This cycle is called the baryon cycle. It regulates star formation, enriches the interstellar medium, and shapes the evolution of the galaxy. Meanwhile, at the heart of many galaxies lies something enormous and quiet, a supermassive black hole. These black holes can be millions or even billions, of times the mass of the sun. How they form is still a question, but we know they grow over time. As gas and stars fall into them, they gain mass. Sometimes, as they feed, they become active. An active galactic nucleus can outshine the rest of the galaxy, emitting jets and radiation across millions of light years. Quasars, the brightest of these nuclei, are among the most luminous objects in the universe. They are beacons from the past, visible even across billions of years of travel. But like all cosmic phenomena, they are temporary. Once the black hole runs out of fuel, it dams, and the galaxy continues on, quieter than before. Today, our own Milky Way is a mid-sized spiral, roughly 100,000 light years across. It contains an estimated 100 to 400 billion stars, and at its center lies a supermassive black hole named Sagittarius A*. Quiet now, but once, it too may have flared with activity. Our galaxy is still evolving. It forms about 1 to 2 stars per year. It moves through space, and it will merge, eventually, with the Andromeda Galaxy. In roughly 4 billion years, the two will collide. They will form a new, larger galaxy, likely elliptical, but no stars will crash. The distances are simply too vast. Instead, gravity will reshape their orbits, and time will smooth out the disruption. In the far future, galaxies will drift apart. The universe's expansion is accelerating. Eventually, distant galaxies will recede faster than light can reach us. Only our local group, a few dozen galaxies, will remain visible. The rest will fade beyond our cosmic horizon. But even then, galaxies will remain shaped by dust, fueled by gas, bound by dark matter, and always drifting. The night sky, to the unaided eye, appears still. But through telescopes, galaxies are never motionless. They spin, they orbit, they collide, and they evolve. Every galaxy is a participant in the vast choreography of the universe, governed by the slow, invisible hand of gravity, and shaped by time beyond our comprehension. Within spiral galaxies, like the Milky Way, stars orbit the galactic center, not in perfect circles, but in gently shifting ellipses. These motions are complex, influenced by the gravitational pull of the central bulge. The surrounding dark matter, halo, and the presence of other stars in interstellar clouds. Over millions of years, these orbits can change subtly, like drifting lanes in a cosmic traffic pattern. Between the stars lies the interstellar medium, a mixture of gas, dust, and cosmic rays. This medium is not uniform. In some regions, it's dense and cool, forming molecular clouds. In others, it's hot and ionized, glowing with the energy of nearby young stars or ancient supernova. The interplay of these different environments determines where and when new stars form. Star formation is not evenly distributed. It tends to happen in bursts, in regions where gas has been compressed by galactic interactions or shock waves from previous generations of stars. These regions often appear as bright knots along the spiral arms, glowing with the light of massive young stars. They shine blue-white, short-lived, but brilliant. Over time, between star formation and feedback from dying stars creates a self-regulating mechanism. Too many stars form at once. The resulting radiation and winds can blow away the remaining gas, pausing further star birth. If too little activity occurs, gas cools and collapses again, triggering a new round of formation. This balance maintains the rhythm of galactic life. Beyond the starry disk lies the galactic halo, a sparse, spherical region containing old stars, globular clusters, and dark matter. The stars here are among the oldest in the galaxy, formed during its earliest epochs. These ancient clusters, orbiting far above and below the disk, provide clues about the galaxy's origin, relics from a time before the spiral structure had settled into place. The dark matter halo, though invisible, dominates the galaxy's mass. It extends far beyond the visible boundaries of the stars and gas. Its presence is inferred through rotation curves, the observation that stars orbit the galaxy at nearly constant speeds, even far from the center. This behavior defies the expectations of visible mass alone. Something unseen, something massive, holds them in place. This hidden component, dark matter, does not clump like normal matter. It forms diffuse halos, smooth and spherical, and interacts only through gravity. It cannot be seen or touched, but it shapes the structure and motion of galaxies at every scale. Without it, galaxies would not hold together. They would simply disperse. In elliptical galaxies, the story is different. These systems lack the ordered rotation of spirals. Their stars move in more random orbits, crisscrossing in all directions. This results in a rounded, featureless appearance. Many ellipticals are found in galaxy clusters, where frequent interactions and mergers erase delicate structures like spiral arms. They are often older, quieter systems with little cold gas and minimal star formation. These galaxies glow with the light of ancient stars, yellow, orange, and red, the slow-burning embers of a more active past. Without new gas, they cannot form many new stars. Instead, they evolve passively, fading gradually as their stellar populations age. Some elliptical galaxies are giants containing trillions of stars. Others are much smaller, dwarf ellipticals, common and faint. Irregular galaxies, though less common, add variety to the cosmic landscape. They often result from gravitational encounters, small galaxies torn apart by larger neighbors, systems disrupted by internal instabilities. Their appearance is chaotic, lacking the symmetry of spirals or the uniformity of ellipticals. Yet they often host intense star formation, fueled by disturbed gas flows and compression. All galaxies, regardless of shape, undergo change. They accrete gas from their surroundings, often funneled in along filaments of a cosmic web. They may capture smaller galaxies in a process called galactic cannibalism, adding their stars and gas to the main body. They experience bursts of star formation, periods of quiescence, sometimes violent collisions. These interactions are not rare. Over the age of the universe, most galaxies have experienced at least one major merger and many minor ones. Night skies full of such events, frozen in time, galaxies caught mid-collision. Their arms stretched, their nuclei glowing, their gas compressed into furious starbursts. These moments are dramatic on cosmic timescales, but they unfold over hundreds of millions of years. As galaxies merge, their structures shift. Disks may be warped or destroyed. New stars may form from compressed gas. Central black holes may be fed and activated. The result may be a new galaxy, larger, more massive, and different in shape. In this way, the galactic population evolves. Spirals become ellipticals. Irregulars become spirals, okay? The universe rearranges itself, slowly, endlessly. The formation of galaxies begins early. After the Big Bang, the universe was a hot, dense plasma. As it cooled, protons and electrons combined to form neutral hydrogen. Tiny variations in density, seeded by quantum fluctuations, grew under gravity. These became the first halos of dark matter. Within them, gas cooled and condensed, forming the earliest stars. These first stars, massive and metal-poor, lived short, intense lives. Their deaths enriched the surrounding gas, making it possible for subsequent stars to form with heavier elements. Over time, these early structures grew and merged, forming the first protogalaxies. From these building blocks, larger galaxies were assembled. This process of hierarchical assembly continues today. Small galaxies fall into larger ones. Gas flows in from the intergalactic medium. Star formation, feedback, and black hole activity shape the internal structure. Galaxies grow more complex, more chemically enriched, and more massive. The Milky Way is a product of this long history. It has consumed smaller galaxies in the past, evidence of which remains in the form of stellar streams and satellite galaxies. It continues to accrete material from the surrounding environment. Its disk is not static. It ripples with waves caused by past interactions. Its halo is populated with remnants of ancient mergers. In the future, the Milky Way will collide with Andromeda. Their combined mass will form a new galaxy, often nicknamed Milkomata. The process will take billions of years. Stars will not collide, but their orbits will change. Gas will be compressed, triggering new star formation. The final product will likely be an elliptical galaxy, larger, more massive, and quieter. Even as galaxies grow, the universe expands. And not just expands, it accelerates. Distant galaxies recede from us faster and faster. Over time, more of them will cross the cosmic horizon, becoming unreachable even at the speed of light. Eventually, only the galaxies within our local group, about 50 or so, will remain visible. The rest will fade into silence, but within that silence, galaxies will endure. They will continue to evolve, to change, to form stars and build worlds. They will remain as beacons in the darkness, complex systems born of gravity, gas, and time. The birth of galaxies is not a single event. It is an ongoing process, driven by the quiet forces of the cosmos. From tiny fluctuations in the early universe to the swirling disks and glowing cores we see today. The story of galaxies is the story of structure itself, how the universe took shape, and in the spaces between stars. In the swirling dust, in the whisper of gas, galaxies continue their slow drift through the fabric of space-time, ancient, luminous, and unending. If you enjoy slow, thoughtful science to drift into rest, consider subscribing to this channel, Fusion Science Sleeps. Tonight, we'll continue drifting gently across the vast darkness, where the architecture of the universe slowly emerges, galaxy by galaxy, light by light, silently folding the early universe into the spirals and swells we see today. In this quiet part of the universe's timeline, billions of years ago, Galaxies weren't yet grand spirals or glowing ellipticals. They were faint, irregular blobs, small clumps of stars and gas drifting within filaments of dark matter. This time is known as the cosmic noon, a poetic phrase for the period when the universe was just a few billion years old, a time of growth, intensity, and radiance, a time when galaxies formed stars at their highest rate, burning through gas reserves to flood the early universe with light. These young galaxies were chaotic. They collided, often interacted with gravitational neighbors, and glowed in the infrared, their light stretched by distance and time. Many were Lyman alpha emitters, galaxies identified by their intense hydrogen emission. Their radiation pierced the neutral hydrogen that still lingered across the cosmos, helping to ionize the universe and make it transparent to light. This process is called cosmic reionization, is a quiet but crucial turning point. Before it, the universe was opaque. After it, galaxies could shine across space. Light could travel, unobstructed for billions of years. The stars of these early galaxies weren't like ours. They were often massive, short-lived, and very hot. They burned through their fuel quickly, exploded as supernova, and seeded the universe with elements heavier than helium, carbon, nitrogen, oxygen, and beyond. In a slow hush of time, these galaxies merged, interacting through complex gravitational dances. Some became larger systems. Some were torn apart. Their stellar populations mixed. Their gas collided, and new stars were born. This cycle of merger, disruption, growth is not a chaotic mess. It is structure, formation, and motion. Each interaction alters the dynamics, some adding angular momentum, others triggering massive waves of star formation. Larger galaxies formed disks, then rotating structures where gas could settle. In these disks, spiral patterns began to emerge. Not solid structures, but density waves, rippling through the galactic plane like slow, tidal shivers. These density waves compress gas as they pass, stimulating the formation of new stars. The bright blue arms of spiral galaxies mark the path of these waves. Each glinting star cluster a flicker in the galaxy's rotation. Over time, star formation continues. The inner regions of galaxies grow denser, forming bulges, spherical concentrations of older stars at the core in the very center. Almost every large galaxy harbors a secret, a supermassive black hole. These black holes, with masses millions or even billions of times that of the sun, are not always active. Many sit quietly, unseen, unfelt. But during the growth of galaxies, some black holes are fed by infalling gas and stars, which spiral inward and disappear beyond the event horizon. As gas falls in, it heats up and emits radiation, sometimes outshining the entire galaxy around it. This is the era of active galactic nuclei, quasars, blazars, and Seyfert galaxies, cosmic lighthouses, beaming across time. It's powered by hunger and gravity. These phenomena are not permanent. Galaxies age. They use up or eject their gas. Star formation slows, and the active centers dim, leaving behind quiet cores surrounded by ancient stars. Yet, even now, galaxies continue to change. Our own Milky Way is still forming stars, still accreting gas, still interacting with its companions. The Sagittarius dwarf galaxy, caught in the Milky Way's gravity, is being slowly consumed. Its stars stretched into streams that wind through our galactic halo beyond our own galaxy. The sky is filled with neighbors. The local group, a small collection of galaxies held together by gravity, includes the Andromeda Galaxy, Triangulum Galaxy, and more than 50 dwarf companions. Andromeda is moving toward us in roughly 4.5 billion years. The Milky Way and Andromeda will merge, not with the crash of stars, but with a gentle blending of orbits, gas, and stellar populations. Simulations suggest the final structure will be more elliptical than spiral. A quiet, massive galaxy formed from the long, slow embrace of two giants across the wider universe. This process is repeated billions of times. Galaxies form, evolve, interact, and merge. Some remain isolated, others cluster together in enormous structures. Galaxy clusters, such as the Virgo cluster or the Coma cluster, contain hundreds to thousands of galaxies, immersed in hot X-ray emitting gas. The space between galaxies is not empty. It is filled with plasma, dark matter, the soft glow of ancient light. Clusters themselves are not stationary. They drift, pulled by dark matter superstructures that stretch for hundreds of millions of light years. These vast structures, filaments, walls, and nodes form the cosmic web. Galaxies reside at the intersections like dewdrops caught in the mesh of invisible threads. This web of matter is the universe's skeleton. Okay? It guides the motion of galaxies, the flow of gas, okay, and the shape of time itself. The deeper we look into space, the further we see into the past. Light from distant galaxies takes billions of years to reach us. And so, the most remote galaxies we can observe are also the youngest. With telescopes like the James Webb Space Telescope, we are now beginning to see galaxies that formed just 300 million years after the Big Bang. Tiny, red-shifted smudges, ancient embers, first islands of light in a sea of darkness. These discoveries help refine our models of galaxy formation. They confirm that galaxies began small, grew through mergers, and gradually developed the complexity we see today. They also reveal surprises, massive galaxies forming earlier than expected. Dusty galaxies with heavy elements present far sooner than models predicted, galactic disks appearing when the universe was still young. Science is rarely about final answers. It is a process of refinement, of updating our understanding as new evidence emerges. And in the stillness of deep space, galaxies continue to send us their light, old light, unfolding across billions of years, arriving now, softly, as if whispered. That light tells the story of structure, the story of how gravity, time, and matter build something larger than stars, larger than planets, larger than any one mind can fully hold. That story, still unfolding, is the story of the cosmos, drifting quietly through the dark. Across this vast, slow-moving tapestry of stars and silence, a single question begins to ripple softly. What governs this galactic order? How do galaxies not fly apart? Why do their stars, spread across hundreds of thousands of light years, continue to orbit instead of dispersing? The answer, whispered in quiet shadows of light, lies not in what is seen, but in what remains unseen, dark matter. An invisible, non-luminous presence that outweighs visible matter many times over. It does not emit light, does not absorb, nor reflect, but its gravity holds galaxies together, preventing their arms from unraveling like loose thread. Without dark matter, the observed rotation of galaxies would be impossible. Stars in the outer regions orbit far too fast. Their speeds defy Newtonian expectations, and yet they remain bound, suspended in orbits defined by a mass that cannot be seen. This hidden scaffolding, a vast halo of dark matter enveloping every galaxy, allows structure to form and persist. It is the silent architect behind spiral arms, bulging cores, and the long tails of colliding systems. Simulations of galactic evolution begin with these halos. Random fluctuations in the early universe, tiny density variations within the cosmic microwave background, slowly pulled in matter, forming the seeds of dark matter halos. Into these halos, gas fell, cooled, condensed, and then formed stars, the first galaxies, cradled in the gravity wells carved by dark matter. And so, in every spiral twist, in every elliptical glow, there is a memory of dark matter's silent guidance. But galaxies are not only shaped by what they contain, they are also shaped by what they expel. Feedback, a gentle scientific word for a violent process. As stars live and die, they push against their environment. Massive stars explode as supernova, releasing shock waves of energy and gas. These explosions stir galactic gas, preventing it from cooling too quickly. They regulate the rate of star formation, ensuring that galaxies don't burn through their gas all at once. And black holes, especially the ones in active galaxies, generate even more powerful feedback. Jets of relativistic particles, winds driven by infalling material, can push out vast reservoirs of gas. In some galaxies, this feedback is strong enough to shut down star formation entirely. Galaxies become quenched. They turn red, filled with old stars, no longer producing new ones. This balance between inflow and outflow, between creation and regulation, defines a galaxy's life. Some galaxies remain star-forming for billions of years. Others form stars in short bursts, then go quiet. Still others flicker back to life when new gas arrives. Over time, these changes accumulate. Galaxies evolve, not like living organisms, but through physical laws and statistical flows. In large surveys of the sky, such as the Sloan Digital Sky Survey, we can map these evolutionary paths. We see blue, star-forming spirals. We see red, quiescent, ellipticals. And we see every stage in between, a slow gradient of color, structure, and light. We also see rare systems, ring galaxies, formed by head-on collisions, tadpole galaxies with bright heads and trailing tails, ultra-diffuse galaxies, barely visible, yet as wide as the Milky Way. These outliers remind us that the universe is not uniform. It is governed by probability, not precision. By variance, not sameness. Every galaxy tells a different version of the same story. And that story does not end when the stars go out. Galaxies, like all cosmic structures, are part of a larger flow. They drift within the cosmic web, influenced by the mass distribution of the universe at large. Simulations like Illustris and Eagle model, billions of years of evolution, showing how galaxies form, merge, and transform within the underlying dark matter network. These models reproduce many observed features: the morphology-density relation, the mass-metallicity relation, the cosmic star formation rate over time, and yet they are not complete. No simulation perfectly matches reality. There are discrepancies, mysteries, uncertainties that persist. Why are some galaxies quenched so early? Why do others form stars efficiently for so long? What role do magnetic fields play in large-scale structure? How exactly does feedback propagate through intergalactic space? These questions are not flaws. They are invitations, signals that the universe still holds secrets and that our understanding, though vast, remains partial. Astronomers use a variety of tools to explore these mysteries. Optical telescopes, like Hubble, show the light of stars. Infrared instruments, like JWST, peer through dust to see earlier times. Radio telescopes map hydrogen gas, tracing the material from which stars are born. X-ray observatories, like Chandra, reveal hot gas in galaxy clusters. Gravitational lensing, the bending of light by massive objects, allows us to detect dark matter indirectly. Together, these instruments assemble a mosaic, a composite portrait of galactic life, woven from many kinds of light. And in quiet observatories, beneath domes turned toward the stars, scientists continue to listen. They measure redshifts, calculate stellar masses, map outflows and inflows, model mergers and disruptions, not to predict every outcome, but to understand the range of possibilities, because galaxies are not just collections of stars. They are laboratories, time capsules, mirrors of cosmic history. Each one contains billions of suns, billions of planets, billions of stories we will never know. Yet, together, they illuminate the shape of the universe, its curvature, its expansion, its fate. And so we continue drifting, through knowledge, through silence, through the slow turning wheel of galactic formation, out in the night sky. Every speck of light is a galaxy in motion, a structure of memory and gravity, spinning slowly in the dark. And all of them, even the ones we cannot see, continue to shape the universe around us. Light travels slowly across the void. It seems immediate to us, a flick of a switch, and the room brightens. But cosmic distances stretch this motion into something else entirely. Every photon that reaches our eyes from another galaxy began its journey millions, sometimes billions of years ago. And so, when we look into the night sky, we are not seeing the universe as it is. We are seeing it as it was. This strange truth is especially important when studying galaxies. The most distant ones we observe are not distant in space alone. They are distant in time. We are seeing them as they looked just a few 100 million years after the Big Bang. These are infant galaxies. Their light is redshifted by the expansion of the universe, stretched from shorter wavelengths into longer ones, until even ultraviolet light becomes infrared. And it is through these stretched out whispers that we glimpse the beginnings of structure. The James Webb Space Telescope, launched in 2021, was built to listen to those whispers. It peers deep into time, capturing faint galaxies at redshifts never reached before. Many of these early galaxies are surprisingly mature, more massive, more organized than models predicted. It has caused scientists to rethink how quickly the first stars and structures could have formed. How fast did gas collapse? How efficiently did it ignite? Some galaxies appear clumpy and chaotic. Others show disks and even spirals. And some may not be galaxies at all, but clusters of stars on their way to becoming one. It is not a fixed process. Galactic birth is not like human birth, with a single moment marking beginning. It is gradual, stretching across epochs, and while some galaxies remain isolated, gently evolving, others collide. Galactic collisions sound violent, and in some ways, they are. Stars do not typically crash into one another, for space within galaxies is mostly empty. But gas clouds interact. Gravity tugs and stretches. Tidal forces distort shapes, triggering bursts of star formation. In the aftermath, new forms emerge. 2. Spiral galaxies may merge into an elliptical one. The collision strips away disks and arms, leaving behind a more uniform spheroidal shape. Starbursts may fade. Supermassive black holes may grow, and the galaxy that remains is no longer what it was. The Milky Way itself is not immune to this process. In about 4 billion years, it will collide with the Andromeda Galaxy. From our point of view, Andromeda is approaching slowly, a faint blur in the northern sky, barely visible to the naked eye on clear nights. But it is falling toward us at 110 kilometers per second. Over millions of years, it will grow larger in the sky. Tidal streams will form. Stars will be flung into wide arcs. Gas will compress and ignite. Eventually, the two galaxies will coalesce, forming a new, larger galaxy that some have nicknamed Milkomeda. To any intelligent beings watching from a safe distance, this collision will be spectacular. Okay, but to life on Earth, it still exists. The changes may be subtle. Stars will continue to shine. Orbits may shift slightly, but the solar system will likely survive intact, gently carried into a new galactic structure. Galaxies of long lifespans, some of the oldest we observe, formed when the universe was less than 1 billion years old, and they have persisted, rotating, merging, evolving for over 13 billion years. Inside them, stars are born, live, and die. These stars forge heavy elements. Hydrogen becomes helium. Helium becomes carbon, oxygen, nitrogen, K. In massive stars, this process continues, creating silicon, iron, and beyond. In supernova explosions, these elements are flung outward, enriching the interstellar medium. It is from this enriched gas that new stars form, and with them, new planets, new chances for complexity, okay? New possibilities for life. In this way, galaxies are not just structures, they are crucibles. Every atom in your body, every calcium atom in your bones, every iron atom in your blood was formed inside a star. That star lived inside a galaxy. T may have been born in a spiral arm, died in a stellar nursery, and scattered its elements across light years. In one day, that matter became you. This is the quiet, drifting truth of cosmic connection. When we speak of galaxies, we do not speak only of things out there. We speak of ourselves. Our sun orbits the center of the Milky Way once every 230 million years. It has done so around 20 times since the solar system formed. Each orbit carries us through different parts of the galactic disk, through arms and air, clouds, through calm and turbulence. It is a long, slow path through a vast, slow structure. And while the galaxy shapes us, we remain unaware. At night, we see the stars, but we do not feel the rotation. We do not sense the drift. It happens gently, without friction, without sound, just motion through gravity, graceful, perpetual, in the stars we see. Most of them are part of our own Milky Way. We do not see far into other galaxies with the naked eye. They are distant, faint, blurred, but with telescopes, we see farther. We see clusters and groups, filaments and voids. We see how galaxies are arranged. They are not spread evenly. They gather into wand, filaments, thread-like structures, stretching across the cosmos. Between these threads are voids, immense regions, nearly empty of matter. This is the cosmic web, a vast, lace-like structure defined by dark matter and the expansion of space. Galaxies form along these filaments. Gas flows along them. Occur where filaments intersect. And over billions of years, the web slowly thickens. It is not a static structure. It changes with time. Galaxies drift. Dark matter accumulates. Its clusters merge. And always light, travels outward, carrying the story with it. This story is written not in words, but in wavelengths, in the stretching of space, in the patterns of star formation, in the absence and presence of certain elements. We read it with instruments, with equations, with stillness, and each discovery leads not to closure, but to more wondering. The galaxies, out there, millions of them, billions, are not a backdrop. They are participants in a quiet unfolding, a universe growing more structured, more entropic, more beautiful with every drift, and as we observe it, through light that took billions of years to arrive. We are not just seeing, we are participating. We are part of the story. Drifting, watching, becoming aware that even in stillness, the cosmos moves. Stars flicker, not just with light, but with motion. They do not sit fixed in space. Even the calmest looking stars we see from Earth are in constant movement. They orbit their galactic centers. They bob up and down through dusty disks, drift apart, collide, realign. Their motion is governed by the invisible gravity, Kadi, dark matter, the subtle push of old collisions. And this motion, measured in tiny shifts of light, tells us where galaxies came from. It's where they are going. When astronomers measure light from a galaxy, they observe not only color, but displacement. Is the light redder than expected? That means the galaxy is moving away. Is it bluer? That means it's coming closer. This is redshift and blue shift, a cosmic Doppler effect. Like the sound of a siren rising or falling as it passes, it's how we know the universe is expanding. Not just galaxies flying away, but space itself stretching. Every centimeter of space gently unfurling, slowly expanding over billions of years. This expansion is not caused by force, but by geometry. The very fabric of space-time stretches like an ever-expanding sheet, and galaxies, caught in that stretching, drift apart. It is this expansion that allows galaxies to form in the very early universe. Everything was too close, too hot, too chaotic. As space expanded, temperature dropped, matter clumped, gravity had room to work, and from those clumps, galaxies began. The first were small. Dark matter halos surrounded them. Hydrogen gas pooled into their centers. Stars flickered to life. But gravity did not stop. Small galaxies merged into larger ones, and those into larger still. This is the process of hierarchical assembly. Galaxies forming from the bottom up, slowly building mass through time. Some galaxies took on spiral shapes, spinning out arms in elegant patterns. Others grew into ellipticals, rounded, featureless, ancient. What determines the shape of a galaxy? In part, it is its history. It formed in isolation, gently spinning. It might become a spiral. If it endured major collisions, it may lose its structure, becoming a featureless cloud. But shape also depends on gas. Its galaxy rich in cold gas can form stars continuously. It maintains blue light, young stars, hot and bright. Its spiral. Arms remain crisp. A galaxy poor in gas cannot make new stars. Its population ages. Stars redden. It becomes quiet, dusty, old. This difference gives rise to the galaxy-colored magnitude diagram, a tool astronomers use to categorize galaxies. On this diagram, you see two major populations, the blue cloud and the red sequence. The blue cloud is where young, star-forming galaxies reside, spirals and irregulars, bursting with motion and energy. The red sequence holds older, more massive galaxies, ellipticals and lenticulars, where star formation has ceased. Between these lies the green valley, a transitional space where galaxies are fading from blue to red, losing their gas, quieting their stars. Why does star formation stop? There are many causes. Sometimes a galaxy simply uses up its gas. Stars form, explode, enrich the surroundings, but no new gas arrives. The galaxy slowly reddens. Sometimes the central supermassive black hole releases energy. It's not by swallowing stars, but through jets and winds that heat the surrounding gas, preventing it from cooling and collapsing. This process is called AGN, feedback, active galactic nucleus activity that regulates growth. Other times, environmental factors play a role. A galaxy falling into a cluster may have its gas stripped by pressure, or it may lose material to gravitational tides, or simply be starved of fresh inflows. Whatever the cause, the result is the same. A galaxy falls silent, and yet even dead galaxies are not truly still. Their stars still move. Their cores still flicker with ancient light. Their halos of dark matter still pull on passing objects. Their central black holes still wait. Galaxies, even when quiet, are alive with memory. Their structure preserves their past. Their light carries the story of formation. Their motion whispers of ancient mergers. Astronomers use simulations to recreate this evolution. Powerful computers, running for weeks or months, simulate the physics of gravity, gas, and light. Projects like Alistris, EAGLE, and Tiang 50 have revealed how galaxies grow, how structures emerge, how clusters form, how the cosmic web evolves. These simulations begin with simple rules: gravity, thermodynamics, hydrodynamics, and from these arise complexity spirals, bars, filaments, mergers. It is a kind of digital universe. It's one we can observe in accelerated time, watching billions of years unfold in minutes. Through these models, we understand that our galaxy is not unique. There are billions like it, and billions not like it. Each one a different story, told through the same laws. Some galaxies are tiny dwarf spheroidals with a few million stars. Others are giants, massive ellipticals with trillions of suns. Some host rich nurseries of star birth. Others are dark, quiet, barely luminous. Some galaxies have bars, linear structures of stars stretching across their centers. These bars may funnel gas inward, feeding black holes or sparking central starbursts. Others show rings, warps, or shells, evidence of past interactions, like ripples in a pond. No two are exactly alike. Even our local group of galaxies shows immense variety. It includes the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and dozens of dwarf satellites. Some of these dwarfs orbit close, bound by gravity, stripped by tides. Others roam further, still part of the group, but largely undisturbed, and all of them together are drifting toward the Virgo cluster, a larger gravitational hub, toward which our local region slowly falls. It is motion on a scale we cannot feel, a billion-year journey across the quiet fabric of space. As we float within the Milky Way, we orbit a center we cannot see. The galactic core is hidden behind thick clouds of dust and gas, but it is there, massive, bright, mysterious dot. At its heart lies a supermassive black hole, Sagittarius A*. It is 4 million times the mass of our sun. Invisible, silent, surrounded by stars that race in tight orbits, their paths traced by years of observation. This black hole does not dominate the galaxy. It is massive, but tiny compared to the whole. Still, it anchors the center, holds clues to the galaxy's history, and, perhaps, to its fate. In the end, galaxies are not eternal. They grow, evolve, fade, stars die. Gas disperses, motion slows, but their light, ancient, drifting light, continues across the cosmos, traveling long after the galaxy's gone, and someone, somewhere, may one day see that light and wonder. From the deep darkness of intergalactic space, we return to the quiet glow of stars, each one a sun in its own right, surrounded by dust, gas, planets or none at all. In each of these stars, from the youngest blue giant to the oldest red dwarf, finds its home within a galaxy. But what truly binds a galaxy together? What prevents it from simply drifting apart in the ever-expanding fabric of space? The answer lies in a substance we cannot see: dark matter. This mysterious component of the universe does not emit light, does not reflect or absorb it. It does not shine, does not flicker, cannot be touched, but it has mass, and it exerts gravity. Dark matter halos surround galaxies like invisible cocoons. They provide the mass needed to keep stars orbiting at the speeds we observe. Without dark matter, spiral galaxies would fly apart. Their outer stars move too fast to be held by visible mass alone. It is the unseen, this dark framework, that holds them steady. Galaxies are born into these halos, before stars, before light. There is the halo. Small clumps of dark matter attract gas, that gas collapses, cools, and eventually stars are born. These halos merge, form larger structures, weaving the cosmic web, a vast scaffold of filaments and voids stretching across the entire observable universe. The cosmic web is not a poetic term, it is literal. Simulations and deep space surveys show an interconnected lattice of matter, with galaxies forming along filaments, clusters at intersections, and enormous voids in between. This structure arises from quantum fluctuations in the early universe, minute differences in density, amplified over billions of years by gravity. Galaxies do not form randomly. They follow these filaments. Gas flows along them, galaxies migrate through them, and clusters form at their densest nodes. In this way, galaxies are not isolated islands, but travelers along invisible rivers of matter. Our own Milky Way lies on such a filament. And though it feels stationary, it is moving. We orbit the galactic center. The Milky Way moves through the local group. The local group drifts toward the Virgo cluster. And beyond that, all of these are being pulled toward a mysterious region of space called the Great ATTRACTOR. This immense gravitational anomaly is not fully understood. It lies behind a dense plane of our galaxy, partially obscured. But observations suggest that thousands of galaxies, entire clusters, are converging toward. It is one of many signs that the universe is not uniform. Structures, while governed by the same laws, form unique, massive, expected configurations. Among these, the galactic cluster is one of the most dramatic. Clusters are the largest gravitationally bound systems. They contain hundreds, sometimes thousands, of galaxies. They are enveloped in hot gas, millions of degrees, visible only in X-rays, and they are permeated by dark matter. Within clusters, galaxies interact frequently. They collide, merge, and sometimes strip each other of gas. These interactions shape their evolution, quenching star formation, altering structure, and changing color. Some galaxies within clusters become seedy galaxies, giants at the center, enormous ellipticals that have consumed many smaller companions. Others become ultra-diffuse galaxies, ghostly faint systems, barely visible. But as large as the Milky Way, their stars are sparse. Their light is dim, but they are real, a reminder of the strange diversity that galaxy formation can produce, in contrast to clusters. Some galaxies are truly isolated. They drift alone in space, far from filaments or nodes. They rarely interact, retain their gas, and evolve slowly. These field galaxies can be pristine, their structures unwarped by collisions. Their histories quiet. They remind us that environment matters, that the same ingredients under different conditions can produce entirely different outcomes. One ingredient that plays a profound role is angular momentum. As gas collapses into a dark matter halo, it often acquires spin, a leftover from tidal forces in the early universe. If that spin is strong, the gas forms a disk. Stars form within it. A spiral galaxy takes shape. If the spin is weak, the gas may collapse more uniformly. Starbursts erupt. Gas is consumed quickly. The result may be an elliptical galaxy. Angular momentum is not the only variable, but it is crucial. It influences structure, star formation, and the likelihood of a galaxy developing arms, bars, or rings. One particularly beautiful structure is the ring galaxy. These form when a smaller galaxy passes directly through the center of a larger disk. The collision sends waves of gas outward, triggering star formation in a circular pattern. The result is a galaxy with a glowing ring of young stars and a quiet center, an echo of the impact that caused it. Galaxies can also host tidal tails, long, luminous streams of stars ripped away during mergers. These tails stretched for thousands of light years, curving through space, sometimes reconnecting, sometimes drifting into the void. They are visible for hundreds of millions of years. Snapshots of violence frozen in starlight. Galactic mergers are common. Our own Milky Way has devoured many smaller galaxies in the past. It bears the scars, stellar streams, warps, odd populations, and in the future will merge with Andromeda. In roughly 4.5 billion years, the two galaxies will collide. Their stars will not crash. The distances are too vast, but their gravity will interact. Gas will compress. Starbursts will flare. And over time, the two spirals will settle into a large elliptical. This future merger is not hypothetical. It is confirmed by measurements of Andromeda's motion, both proper motion and redshift. Astronomers can simulate the collision. They can predict the likely outcomes, and they can watch, in other parts of the sky, galaxies undergoing this process. Today, these interactions are not just disruptions. They are part of growth. They allow galaxies to evolve. They mix populations, redistribute gas, and change structure. Even our solar system owes its existence to ancient mergers, for it is likely that the gas cloud that formed it was enriched by past collisions. In every direction, we see evidence of motion. Galaxies are never still. Quote, stretch, compress, expand. Some are caught in cycles, forming stars, burning bright, then fading. Others drift slowly, quiet and dark, barely changing. And some, like our Milky Way, are alive with motion and time. History, spiral arms turning, stars circling, clouds collapsing. At the largest scale, the universe continues to expand. The space between galaxies grows. The light from the earliest galaxies shifts ever redder, fainter, until one day it will slip beyond visibility. But for now, we can still see them. We can still trace their shapes. We can still read their stories in the color of their stars, the bend of their arms, the structure of their halos, and we can still wonder how galaxies are born, how they live, and how they drift through the quiet dark of the cosmos. The galaxies we see in the night sky are not frozen relics. They are in motion. Each one is part of a larger story, a process of continual change, transformation shaped by physics, by gravity, by time. But to understand how galaxies evolve, we must consider what happens within them, within their cores, their disks, and their hidden black hearts. At the center of nearly every large galaxy, including the Milky Way, resides a supermassive black hole. These are not the black holes formed by collapsing stars. They are vastly larger, millions or even billions times the mass of our sun. How these black holes formed is still under study. There are several theories. One possibility is that they began as massive seed black holes, formed directly from collapsing clouds of gas in the early universe, bypassing the usual process of stellar death. Another theory suggests that smaller black holes grew rapidly through accretion, drawing in matter from their surroundings and merging with other black holes until they reached immense size. However, they began. We know that supermassive black holes are common, and they are not passive. When matter falls toward them, it forms an accretion disk, a spinning, superheated disk of gas and dust. Friction in the disk causes it to radiate. The brightest of these are active galactic nuclei, or AGNs. Some AGNs are so luminous that they outshine their entire host galaxy. They emit powerful jets, beams of charged particles launched perpendicular to the disk at nearly the speed of light. These jets can extend for hundreds of thousands of light-years in their most extreme form. They become quasars. Quasars were first discovered as strange, star-like objects with unusually strong radio signals. Only later did astronomers realize they were the brilliant centers of distant galaxies, so far away that their light had taken billions of years to reach us during their active phase. Quasars can halt star formation by heating or blowing away interstellar gas. This process is known as feedback. Black holes, though small in size, can regulate the evolution of entire galaxies. Eventually, as they exhaust nearby fuel, they quiet. The jets fade. The AGN goes dormant, but the black hole remains, silently waiting at the heart of the galaxy. In some galaxies, we observe signs of past activity, bubbles of X-ray emission, relic jets, disturbed gas. Our own Milky Way contains a central black hole called Sagittarius A*. It is currently quiet, but evidence suggests that it may have been more active in the past. High-energy outbursts, perhaps millions of years ago, sent shock waves into our galactic halo, visible today as faint Fermi bubbles extending above and below the galactic plane. These ancient echoes remind us that even galaxies that appear still may have once roared with energy beyond their central engines. Galaxies change through more subtle processes. One such process is secular evolution. Unlike violent mergers, secular evolution occurs gradually. Over billions of years, the internal structures of galaxies can shift and change. Bars may form in spiral galaxies, funneling gas inward, feeding central starbursts or black holes. Disks may become thicker, arms may wind tighter or looser. Some spiral galaxies become lenticular galaxies, intermediate between spirals and ellipticals. They lose their gas, stop forming stars, and their structure becomes smoother. Galaxies also age through the consumption of gas. Stars form from cold gas, and when the gas is gone, star formation ceases without fresh infall from the cosmic web. A galaxy slowly transitions from blue and active to red and quiescent. This shift is called galactic quenching. Galaxies on the cusp of this transition lie in what astronomers call the green valley. Neither is fully star-forming nor fully passive. Eventually, most galaxies move into the red sequence, a region on the colored magnitude diagram where older, redder galaxies reside. But this progression is not always one way. Some galaxies can rejuvenate, a minor merger, a flow of gas, a new burst of star formation. These can move a galaxy back into activity. Galaxies are dynamic. They evolve. They shift between states. But no matter their path, each one contributes to the larger narrative of the cosmos. We studied their light, their shapes, their motion, and we find patterns. The Hubble sequence, first developed by Edwin Hubble, categorizes galaxies by morphology: spirals, ellipticals, lenticulars, regulars. While it was once thought to represent an evolutionary path, we now know it's more of a classification system. Still, these shapes tell us something. Spiral galaxies are usually younger, rich in gas, forming stars. Ellipticals are older, gasper, quiet. Irregulars may be dwarf galaxies, or the result of interactions. But each one is part of the galactic zoo, a term that captures the variety, complexity of the universe's building blocks. This variety extends beyond the visible galaxies, emit in all wavelengths, not just optical light. Radio telescopes reveal jets and pulsars. Infrared detects dust-shrouded starbursts. Ultraviolet shows young, hot stars. X-rays uncover hot gas and black holes. Multi-wavelength astronomy gives us a more complete picture, and with each observation, our understanding grows. Modern surveys, like the Sloan Digital Sky Survey and Galaxies, have mapped millions of galaxies. New instruments, like JWST, are peering into the earliest epochs. They capture galaxies as they were less than 1 billion years after the Big Bang. These young galaxies are often clumpy, turbulent, forming stars at high rates. They show us the universe in its youth, a time of rapid formation, of frequent mergers, of intense activity. And as we compare them to galaxies today, we trace the arc of cosmic history. We see how galaxies grow, how they settle, how they fade. Even now, some galaxies are being born in small halos at the edges of voids. They begin as faint smudges, gather gas, spark stars. They are new entries in a very old ledger. Meanwhile, others die. They exhaust their gas. Their stars age. They grow dim. Yet, even in death, they contribute. They merge. They recycle. Galaxies are not eternal, but their lifespans are vast. They endure for billions of years. They drift, ply, they transform. And in their light, we find clues to the nature of space, of time, of origin. The study of galaxies is not just about distant objects. It is about understanding where we come from, our solar system, our planet. Even our atoms were born from galactic processes. We are stardust recycled through generations of stars, through the spiral arms of a galaxy that has traveled through space for over 13 billion years. And we are not alone. There are trillions of galaxies, each one with stars, perhaps planets, perhaps life, each one drifting through the cosmos. carrying with it the quiet echoes of its birth, the deep rhythm of gravity, and the silent beauty of the universe unfolding. The deeper astronomers look into the universe, the further back in time they see. This is not a metaphor. It is a consequence of how light travels, because light moves at a finite speed, about 299,792 kilometers per second. When we observe distant galaxies, we are seeing them as they were millions or billions of years ago. This allows researchers to study the evolution of galaxies directly by comparing those far away and young to those nearby and old. The Hubble Space Telescope, with its deep field images, revealed galaxies from just a few 100 million years after the Big Bang. These galaxies appear small, chaotic, irregular. Their shapes are not yet well defined. They are clumpy, with intense regions of star formation. This early phase of galactic life is sometimes referred to as cosmic dawn. In this epoch, hydrogen clouds cooled, collapsed, and began to form the first stars. The ultraviolet radiation from these newborn stars ionized the surrounding hydrogen, a process known as cosmic reionization. Reionization marks the end of the so-called dark ages of the universe, when the cosmos was filled with neutral hydrogen and no visible light could propagate far. This transformation from a foggy, opaque universe to one transparent and starlit occurred over a span of several 100 million years, and it was driven by the energy of young galaxies and quasars. But galaxies did not appear all at once. They built up gradually. Small proto-galaxies formed first clumps of stars and gas, held together by dark matter. Over time, they merged, combined, and grew more massive. Simulations like Illustris and Eagle have shown how galaxies evolved within a network of cosmic filaments. Gravity pulled matter into dense knots, and galaxies emerged at the intersections of these filaments. This web-like structure, called the cosmic web, is composed primarily of dark matter. Though invisible, dark matter provides the scaffolding upon which galaxies form. It outweighs normal matter by a factor of 5 or more. Without it, the universe would look very different. Galaxies clustered along the filaments, swarm chains, walls, and superclusters, like the Sloan Great Wall, one of the largest known structures in the universe. Between these filaments lie enormous voids, regions almost completely empty of galaxies. This large-scale structure was imprinted by the slight density fluctuations in the very early universe, amplified by gravity over billions of years. Galaxies are thus not isolated islands. They are part of a vast, interconnected landscape. Their individual fates, however, are shaped by local processes. Some galaxies merge and grow. Others lose their gas to nearby giants. Some are stripped by tides. Others are canibalized. The environment matters. Galaxies in dense clusters often evolve differently than those in the field. Cluster galaxies are subject to ram pressure stripping, a process in which the hot gas of the cluster pushes against a galaxy moving through it, blowing away its interstellar gas. This can shut down star formation and transform spirals into ellipticals. Galaxies in clusters also interact more frequently, colliding, merging, or being distorted by tidal forces. The central galaxy in a cluster, often the brightest, is called the brightest cluster galaxy BCG. These giants are usually massive ellipticals, sitting at the cluster's gravitational center, fed by the surrounding gas and by the remains of smaller galaxies. One such example is M87, the BCG of the Virgo cluster, and a home of the first imaged black hole. In contrast, galaxies in more isolated regions can continue forming stars for much longer. They accrete gas from the intergalactic medium, sometimes along cold streams that feed their disks and sustain spiral structure. These differences remind us that galaxy evolution is not one size fits all. It is a diverse process, shaped by internal mechanics and external context. Within galaxies, stars form in molecular clouds, cold, dense regions of gas and dust. These clouds collapse under gravity, fragment, and give birth to stellar nurseries. Massive stars live fast and die young. They go supernova within a few million years, injecting energy back into their surroundings. This feedback regulates star formation, clearing out gas and creating complex cycles of destruction and renewal. In some regions, this balance leads to galactic fountains, streams of gas ejected from the disk only to cool and fall back later. In others, it results in galactic winds, outflows that escape the galaxy entirely, enriching the intergalactic medium with heavy elements. These processes ensure that no galaxy remains static. Even quiescent galaxies contain billions of stars, each following its own path, each orbiting the galactic center in vast elliptical loops. In the Milky Way, our solar system orbits the center once every 230 million years, a period known as a galactic year. Since the formation of Earth, the Sun has completed only about 20 such orbits. Galaxies, then, are not fixed. They spin, they pulse, they breathe. The Milky Way itself is part of the local group, a collection of more than 50 galaxies, including the Andromeda Galaxy, the Triangulum Galaxy, and many dwarf galaxies. The local group is gravitationally bound. Over time, its members will drift closer in about 4 billion years. The Milky Way and Andromeda are expected to collide. This future merger will not result in stars crashing into each other. The space between them is too vast. Instead, the galaxies will pass through one another, distort, shed stars, and eventually coalesce. The result will likely be a giant elliptical galaxy, sometimes called Milkomata. Long after the merger, star formation may slow, the galaxy will settle, and its spiral structure will vanish. But in the grand timeline of the cosmos, this is just another phase. Galaxies come together, they change form, they continue their quiet drift through expanding space, and all the while, the universe cools, the stars burn, the light fades. Can galaxies continue their slow evolution, beautiful, silent, ancient? As we drift deeper into the cosmic night, a quiet question begins to echo. Where does the energy come from that powers a galaxy for billions of years? Much of the answer lies in the quiet machinery of stars. But not all galaxies are governed only by the silent fusion of hydrogen. Some, at their centers, harbor something more, a presence, darker, heavier, a gravitational well so deep that even light cannot escape. These are supermassive black holes, and they reside in the heart of nearly every large galaxy we observe. In ordinary times, they lie dormant, invisible. But when a galaxy's core becomes crowded, when gas, dust, stars are drawn inward, the black hole awakens. It begins to feed. This process is called accretion, as matter spirals inward. It forms a disk, flattened by angular momentum, heated by friction, and glowing across the electromagnetic spectrum. The core becomes a quasar, or a Seyfert galaxy, or a blazar, depending on the angle from which we observe. Together, these are known as active galactic nuclei, AGN. In the early universe, quasars were far more common. We see them shining from billions of light years away, their brilliant jets stretching across intergalactic space. Despite their distance, they shape their host galaxies. The energy released from a GN can heat the surrounding gas, preventing it from cooling, thus halting star formation. This is called feedback, a self-regulating mechanism that keeps galaxies from growing indefinitely. It may explain why massive galaxies often have less star formation than smaller, irregular ones. The relationship between galaxies and black holes is complex, but it is now believed they co-evolve. The mass of a galaxy's central black hole tends to correlate with the size of its bulge. a quiet clue that the two have influenced each other across billions of years. Galaxies are not mere star clusters. They are ecosystems, self-organizing, self-regulating, and dynamic. In their disks, spiral arms trace patterns of density regions where gas is compressed, triggering star formation, then fading again. In their halos, globular clusters orbit like ancient satellites containing some of the oldest stars in the universe. Outside the visible disk, an enormous sphere of dark matter extends invisible, undetectable by light, but inferred from motion. Without this halo, the outer stars of galaxies would fly apart. Their observed velocities require more gravity than normal matter provides. This dark matter is one of the great mysteries of modern cosmology. We do not know its composition, but we see its fingerprints everywhere in galactic rotation curves, in gravitational lensing, the distribution of cosmic structure. Without dark matter, the universe would be smoother, quieter, less structured. Its invisible scaffolding has cradled galaxies from their birth. Galaxies age. They consume their gas. Star formation slows. They grow redder, fainter, quieter. Some transition into elliptical forms, with little gas or dust, populated by older stars. Others, disrupted by mergers, are reshaped into lenticular galaxies, a transitional form between spiral and elliptical. And some remain spirals for billions of years. It's like our own Milky Way, sustained by gentle infall of gas from the intergalactic medium. But even they are not immune to time. Cosmic rays, supernova winds, and the gentle leaking of gravitational energy all contribute to a slow fading dot in the far future. Galaxies may become cold, dim shells of ancient stars and compact remnants, and the space between them will grow ever wider, because the universe is not static, it is expanding. First discovered by Edwin Hubble, this expansion is now seen as accelerating, driven by a mysterious force called dark energy. Dark energy acts like a negative pressure, pushing galaxies apart faster and faster. As time stretches forward, more galaxies will pass beyond our horizon. Their light will no longer reach us. The universe will become quieter, LONELIER, in 1 trillion years. Only the galaxies gravitationally bound to us will remain visible. The rest will have vanished beyond reach. This concept, the heat death of the universe, is not dramatic, not catastrophic. It is slow, gentle, unfolding over eons. Galaxies will fade. Stars will burn out. Black holes will evaporate, and space itself will become cold and still. But we are not there yet. We live in a bright age when galaxies still collide, when stars still form, when light still travels across the void. And in this moment, we look outward and inward. We map galaxies, we classify their types, we measure their spectra, their redshifts, their chemical compositions. Each data point adds brushstroke to the canvas of the cosmos. We learn that spiral galaxies often show blue hues, signs of active star formation. We learn that elliptical galaxies tend to be redder, dominated by older stars. We learn how mergers trigger bursts of star formation, followed by long declines. We study galaxies in every wavelength, from radio to gamma rays, to see the full picture. In radio, we trace cold hydrogen gas. In infrared, we see dust-skewered star formation. In X-rays, we detect hot gas and Aegean, invisible light. We observe starlight itself, and now, with instruments like the James Webb Space Telescope, we see galaxies as they were in the earliest times. We peer back over 13 billion years, witnessing structures just beginning to form, stars just beginning to burn. The universe unfolds before us like an ancient scroll, its stories written in light, its patterns etched across space and time. Galaxies are not just distant objects, they are archives. Each one holds a history of motion, of transformation, of elemental cycles, from hydrogen to helium to carbon to oxygen, to the calcium in our bones and the iron in our blood, all forged in stars, scattered by galaxies. We are not separate from them. We are their quiet offspring, born of ancient light. To understand the life cycle of galaxies more deeply, we can trace their stories not just through form and color, but through elemental evolution. Galaxies are the crucibles in which elements are forged. Stars form, live, and die within them. The fabric of the galaxy becomes richer and more complex over time in the early universe. Shortly after the Big Bang, there were only a few elements, primarily hydrogen and helium, with trace amounts of lithium and beryllium. These primordial elements were formed during the first few minutes after the universe began, period known as Big Bang nucleosynthesis. Galaxies are the environments in which heavier elements called metals in astrophysical terms begin to appear. These metals are formed within stars through the process of nuclear fusion. In massive stars, lighter nuclei like carbon and oxygen are fused into heavier ones like silicon, sulfur, and eventually iron. When these massive stars end their lives in supernova explosions, the newly formed elements are scattered into the interstellar medium. Over time, new generations of stars are born from this enriched gas. The metallicity, the abundance of elements heavier than helium of a galaxy, increases. Thus, older galaxies or regions that have undergone many cycles of star birth and death tend to have higher metallicities. This process of chemical enrichment serves as a kind of galactic memory, encoding the number of stellar generations that have come before. Astronomers measure this metallicity through the absorption and emission lines in a galaxy spectrum. Specific wavelengths of light are absorbed or emitted by different elements, allowing scientists to determine the chemical composition of distant systems. These measurements have shown that galaxies evolve chemically just as they do structurally, and dynamically. Galactic metallicity also affects star formation. Gas with higher metallicity cools more efficiently, allowing it to collapse into stars more easily. But too many metals can also lead to the formation of small, dense clumps that fragment excessively, potentially altering the distribution of stellar mass, a process known as the initial mass function. Thus, the balance of elements in a galaxy influences its future. Dust, too, plays a role. Formed from the remnants of dying stars, interstellar dust grains absorb and scatter light. This dust not only dims the starlight we observe, but also contributes to the cooling of interstellar gas. In dense molecular clouds, dust acts as a catalyst, enabling the formation of complex molecules and shielding them from destructive radiation. In many galaxies, these dust-rich regions become stellar nurseries where new stars ignite in clusters. Observing these regions in infrared wavelengths allows us to peer through the dust and witness the early stages of stellar life. Some galaxies, however, have very little dust and gas. These are often older, elliptical galaxies, where star formation has largely ceased. The stars within them are typically older and redder, and the galaxy glows with the faint, warm light of ancient suns. But others, starburst galaxies, undergo intense, short-lived periods of star formation. These bursts may be triggered by interactions or mergers with other galaxies, compressing gas and dust and igniting rapid stellar birth. Starbursts can form stars hundreds of times faster than typical spiral galaxies. However, this activity is unsustainable. Once the gas is consumed or driven out by feedback from supernova and stellar winds, star formation slows dramatically. Galactic wind streams of gas and dust blown out of galaxies also played a role in regulating their evolution. These winds can be driven by supernova explosions or by the powerful radiation and jets from active galactic nuclei. In some cases, they can carry metals into the intergalactic medium, enriching the space between galaxies and shaping the environment for future galaxy formation. In clusters of galaxies, the interplay between individual systems becomes even more complex. Clusters are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies, along with hot gas and dark matter. Within these clusters, galaxies interact through gravity and hydrodynamics. They can merge, be stripped of their gas through ramp pressure stripping, or have their orbits perturbed by gravitational encounters. These processes can quench star formation and alter galactic structure, accelerating their evolution. The space between galaxies and clusters is not empty. It is filled with hot, X-ray emitting gas, known as the intracluster medium. This gas is enriched with elements from countless supernova and galactic winds, providing a fossil record of past activity. We also see evidence that galaxies evolve differently in dense environments compared to more isolated settings. In clusters, galaxies are more likely to be ellipticals or lenticulars with less gas and lower star formation rates. In the field regions of lower galactic densities, pyrogalaxies are more common, often with active star formation. This suggests that environment plays a crucial role in galactic evolution, but across all environments, galaxies obey certain pattern scaling relations that link mass, luminosity, metallicity, and other properties. The Tully-Fisher relation, for example, links the rotational speed of a spiral galaxy to its luminosity. The Faber-Jackson relation connects the velocity dispersion of stars in an elliptical galaxy to its brightness. These patterns hint at underlying physical laws governing galaxy formation and evolution, laws rooted in gravity, thermodynamics, and hydrodynamics today with modern telescopes and simulations. Astronomers can trace these patterns back to the earliest epochs of cosmic time. Observatories like the Hubble Space Telescope and James Webb Space Telescope have revealed galaxies as they appeared just a few 100 million years after the Big Bang. These infant galaxies are small, irregular, and often undergoing intense star formation. Their light, stretched by the expansion of the universe, arrives at Earth in infrared wavelengths. Analyzing this light allows us to reconstruct their structure, star formation rates, its chemical compositions. Simulations like Illustris and Eagle attempt to model the formation and evolution of galaxies over cosmic time, incorporating gravity, hydrodynamics, and feedback processes. These models are compared with observations to refine our understanding and test theories. From these studies, we've learned that galaxy formation is hierarchical. Small structures form first, merging over time to build larger ones. This bottom-up scenario matches the predictions of the Lambda, cold, dark matter, CDM, cosmological model. But many questions remain. We still do not fully understand the nature of dark matter or dark energy. We don't yet know why some galaxies evolve rapidly while others remain stable for billions of years. The processes governing feedback, star formation, chemical enrichment are complex and not yet fully constrained. Yet, with every observation, every spectrum, every simulation frame, we draw a little closer to understanding how galaxies are born, how they live, and how they die. As we observe the light from galaxies across billions of light years, we are also looking back in time. The farther we look, the younger the universe appears. Galaxies seen at high redshift are snapshots of earlier stages in their evolution. In this way, the cosmos becomes a kind of time machine, layered archive of creation, collapse, and rebirth. Galaxies do not simply exist. They grow, change, interact, and fade. They are storytellers in the language of gravity and light. Their spiral arms are not, just patterns, but records of motion. Their elliptical halos are not just shapes, but remnants of ancient collisions. Their colors are not mere hues, but signatures of age, composition, and process. And within them, through countless stars and dying suns, they have given birth to planets, to chemistry, to life, and to beings that can now look back and wonder how it all began. When we look deeper into the mechanics of galaxy formation, we arrive at the underlying framework that holds everything together: dark matter halos. These invisible scaffolds shape the universe, guiding the assembly of galaxies from the earliest times. While dark matter doesn't emit or absorb light, its presence is inferred through gravitational effects. It bends light around it, alters orbital speeds, shapes the large-scale structure of the cosmos in the standard CDM model, lambda. Cold, dark matter. Galaxies form inside these halos of dark matter. As the universe expands, slight fluctuations in the density of matter cause some regions to collapse under gravity. These denser pockets become gravitational wells, pulling in surrounding gas and dark matter to form halos. Within these halos, gas cools, condenses, and eventually forms stars. This is how galaxies begin. The nature of dark matter remains elusive. It neither shines nor interacts strongly with normal matter. Yet, it makes up roughly 85% of the total matter in the universe. Without it, galaxies would not hold together. Their stars would fly apart. Dark matter acts as the gravitational glue that anchors galactic structures and determines their rotation curves. This invisible framework also explains why galaxies clustered away. They do in filaments, sheets, and voids that stretch across cosmic distances. The cosmic web, as it's known, is a vast interconnected structure made primarily of dark matter, with galaxies forming along its dense threads at the intersections of these filaments, where the gravitational forces are strongest. We often find clusters of galaxies, the nodes of the web. These regions are especially rich in interactions, mergers, and high-energy processes that shape galaxy evolution. But while dark matter forms the skeleton, it's the baryonic matter, the atoms we're made of, that fills in the body. Stars, gas, dust, all of it resides within the framework shaped by dark matter halos, the process of baryonic collapse inside. These halos is complex and sensitive to many variables: the amount of gas, the rate of cooling, the influence of stellar feedback, and the presence of black holes. Cooling is one of the critical steps. When gas falls into a dark matter halo, it heats up. To condense and form stars, it must cool. In the early universe, this cooling was aided primarily by atomic transitions in hydrogen and helium. Later, as metals enriched the gas, radiative cooling became more efficient, especially through molecules and fine structure lines. This allowed gas to collapse into molecular clouds, dense, cold regions where stars could begin to form. These clouds are shaped by turbulence, magnetic fields, and gravity, leading to fragmentation and the birth of stellar clusters. Not all galaxies form stars at the same rate. Some undergo bursts of activity. Others slowly churn out stars over billions of years. And some, for reasons still under study, stop forming stars altogether. This brings us to quenching the process by which a galaxy halts its star formation. There are several possible causes. In dense environments, like galaxy clusters, ramp pressure stripping can remove a galaxy's gas as it moves through the hot intracluster medium. Major mergers can trigger intense starbursts, rapidly consuming available gas and leaving the galaxy starved. Feedback from supermassive black holes in the form of powerful jets or radiation can heat or expel gas, preventing it from cooling and condensing. These processes can transform a star-forming spiral, this galaxy, into a quiescent elliptical one. The structure changes, the color shifts from blue to red, and the galaxy begins to fade, not because stars are dying faster, but because new ones are no longer being born. Still, not all galaxies follow this pattern. Some are green valley galaxies, in transition between blue star forming and red passive types. Studying these systems helps astronomers understand the timeline and mechanics of quenching. Meanwhile, galaxies don't exist in isolation, okay? Many have satellite galaxies, smaller systems that orbit them like moons around a planet. These satellites can be drawn in and absorbed through a process known as galactic cannibalism. Over time, large galaxies grow by merging with and consuming smaller ones. This hierarchical growth is central to galaxy evolution. Every major galaxy today is the product of many smaller mergers. These interactions are not always violent. Some are slow, graceful dances where the galaxies spiral around each other for billions of years before becoming one. But in other cases, the collisions are dramatic. Gas clouds crash and compress, triggering massive starbursts. Gravitational forces stretch and warp the galactic disks into tidal tails. In some mergers, the supermassive black holes at the centers of both galaxies eventually collide, releasing enormous energy in the form of gravitational waves, ripples in space-time itself. These black hole mergers are rare, but they offer a profound window into the extremes of physics. Observatories like LIGO and Virgo have detected these events, confirming predictions made by Einstein a century ago. At the centers of most galaxies lies a supermassive black hole, millions or billions of times the mass of the Sun. While their exact role in galaxy formation is still debated, evidence suggests a strong connection between black hole mass and the properties of the host galaxy. The M-sigma relation, for example, shows a tight correlation between the mass of the central black hole and the velocity dispersion of stars in the galactic bulge. This hints at a coevolution, a feedback loop where the growth of the black hole regulates and is regulated by the growth of the galaxy. An active galactic nuclei, AGN. The black hole is accreting material, gas and dust, spiraling inward and forming an accretion disk. This process releases tremendous energy, sometimes outshining the entire galaxy. The radiation and jets from AGNs can heat or expel gas, affecting star formation on galactic scales in extreme cases. These AGNs are called quasars, among the brightest objects in the universe. Quasars are typically found at high redshifts, indicating that they were more common in the early universe. They represent a phase in galactic life where the central black hole is growing rapidly, often during or after a major merger. As galaxies age, their activity levels tend to decline. Star formation slows, black hole growth tapers off, and the systems settle into more stable configurations. Still, galaxies remain dynamic. Stars orbit within them, moving in patterns shaped by the galaxy's mass distribution. Spiral galaxies exhibit orderly rotation. Elliptical galaxies have more randomized stellar motions. Gas continues to flow in from the intergalactic mediums, sometimes fueling renewed star formation and cosmic events, like the merger between the Milky Way and the Andromeda Galaxy, predicted to occur in about 4 billion years, remind us that even galaxies are not eternal. In that far future collision, the two spirals will become a single, larger elliptical galaxy. Their stars will largely pass by one another due to the vast distances between them. But gas clouds will collide, triggering new starbursts. Central black holes may merge, and the resulting galaxy, sometimes called Milkomeda, be a testament to the endless reshaping of the cosmos. All of this is guided by the same fundamental forces that govern the smallest particles: gravity, thermodynamics, radiation, and time. From primordial fluctuations to luminous spirals, from dark matter halos to quasars burning bright, from gas collapsing in silence to galaxies dancing in light. The universe creates over and over again. Each galaxy is a moment in that grand process. Each star is a flicker of the universe remembering itself. Each observation is a step closer to understanding who we are and how everything began. Good night.